Welcome back to our machine design series. Today we are talking about epicyclic gear sets. These are also sometimes called planetary gear sets, and they are characterized by the fact that they have one or more gears that don't have fixed axes of rotation. And this can result in some unusual effects because they have 2 degrees of freedom. So for any type of motion, a planetary gear train or an epicyclic gear set needs to have 2 inputs. So let's look at an example of this. All right, so here's an example planetary gear train with really 4 gears on it. First one is called the sun gear. It's called that because everything else rotates around this sun. And then we have number 3, which is our arm gear. Our arm gear is often the output of an epicyclic gear train. And then we have a planet gear. This planet rotates around the sun, is connected to the sun by the arm. And then lastly, we have our ring gear. Okay, so as we said, you have to have 2 inputs to define the motion of this epicyclic gear set. So, for example, we might say that the sun gear is going to rotate clockwise at some specific speed n2, and we'd maybe say that the ring gear is going to rotate counterclockwise with a speed n5. And with those 2 inputs defined, then we are going to be able to find the output, which is in this case going to be the motion of the arm gear. So this is just one example. There are many different types of orientations you might see of these epicyclic gear sets. So let's look at another example, one that is a little bit more similar to things that we've seen before. Okay, so here's another setup that you might have for a planetary gear train. And now let's start relating some of these angular velocities to one another. So we know that the angular velocity of gear 2 relative to gear 3 is just going to be equal to the speed of gear 2 minus the speed of gear 3. This is just standard relative motion, or the relative velocity of gear 2 to 3 is just one minus the other. Now we can write the same thing for the velocity of gear 5 relative to gear 3. Could say that it is n5 minus n3. And then if we think about this gear train in a similar way to the gear trains that we saw in the previous video, we were initially setting these up, we can write now our train value as the ratio of n5 relative to 3 divided by n2 relative to 3, which is going to be n5 minus n3 over n2 minus n3. Okay, and written another way, we could say that in general, our train value is equal to the speed of the last minus the speed of the arm divided by the speed of the first minus the speed of the arm. And if I were to fix the arm, hold the arm in place, then you can see that the speed of the arm would just be 0, right? If I'm holding the arm in place, the speed of that arm is 0. And this equation becomes the same as the equation we had for the train value up here, where the speed of the last is equal to the train value times the speed of the first. So if we let the speed of the arm be 0, then the speed of the first can be brought over here. We have the same equation. The speed of the last is equal to the train value times the speed of the first. So the only thing that we're changing when talking about these epicyclic gear sets is that we have to have two inputs. So we have to define relative motion between multiple gears in the gear train. Okay, and that's also related to the number of teeth on the first and last gears. In this case, letting the first gear be the sun and the last gear be the ring. And you'll notice that we have this plus minus sign. So again, we have to figure out the direction of the input and output gears to figure out whether we have a positive or negative train value, as we did with standard gear sets in the previous video. And the sign is going to, again, just tell you whether the first and last gears are rotating in the same direction or in the opposite directions. And the easiest way to do this is to hold the arm stationary and rotate the first gear and then see if the last gear rotates in the same direction or in the opposite direction. And this is easier to do if you have a physical gear set that you can hold on to, hold the arm steady. But for example, in this drawing up here, if I hold the arm stationary, then I can treat this as like a regular gear train, where if N2 is rotating clockwise, N4 will be counterclockwise, and 5 would be clockwise, so they're going the same direction on the input and output, which means that the train value should be positive. All right, so let's do an example using this drawing up here. Okay, so in this example, we're told that the speed of the sun gear is 100 RPM. We'll use the same direction that we had before, so it's 100 revolutions per minute clockwise. We are now going to attach the ring gear to the frame so that it is not rotating. And the question asks us to find the speed of gear 3, which is just the arm, and the speed of gear 4, which is our planet gear. So to find our train value, first we're going to sort of unlock gear 5, which is the ring gear, and fix the arm. When we do that, the planet gear 4 and the ring gear 5, they're going to rotate in the same direction, opposite of the sun gear, right? So if I think about the way that the sun gear and the planet gears are meshing together, we have to have that this pitch line velocity is the same for gears 2 and 4, and so that means that gear 4 must be rotating counterclockwise. If gear 5 is then unlocked, it is going to also rotate in the same direction as gear 4. And that's because gear 4 is an internal gear to gear 5. So our train value is going to be negative. Okay, we did all that just to work out whether our train value was going to be negative or positive. Another way that you could see this is by counting the number of meshes, but when you do that for a planetary gear set, we don't count the internal ring gear. So if I count the number of internal meshes, I just have 1, which means that this is going to be a negative train value. And we don't count the internal mesh because they're going to go in the same direction, and internal gear is going to go in the same rotation direction. All right, so now let's write our train value. Okay, and I meant to define the number of teeth as part of the givens, so let's do that now, because you're going to need that to find the actual train value. Okay, so we have 20 teeth on the sun gear. We don't have a number of teeth on gear 3. It's just an arm that connects 2 and 4. Gear 4 has 30 teeth, and gear 5, the ring gear, has 80 teeth. So now let's plug this in down here. We have negative 20 divided by 30 times 30 divided by 80. So our train value is going to be negative 1/4. Okay, now let's substitute this train value into our equation up here. The speed of our last gear is the ring gear. We've fixed it, so it's 0. The speed of the arm is what we're trying to find. The speed of the first gear was given as 100 RPM clockwise, which is negative. We define clockwise as negative, minus NA. You don't have to define clockwise as negative, but that's common convention. So we can solve this equation now for NA. We find that the speed of the arm is negative 20 RPM, which is the same as saying that it is 20 RPM clockwise. Now to obtain the speed of gear 4, we can follow the same procedure that we used to obtain this equation originally and write the relative speed of gear 4 with respect to the arm. Gear 3 is going to be N4 minus N3. Oh, I should have written, this is not train value, this is speed. And the relative speed of 2 with respect to 3 is still N2 minus N3. So now that ratio, N4 3 over N2 3 is N4 minus N3 over N2 minus N3. Okay, and now we're going to look at our gear train again, and this time we're going to sort of ignore the ring gear, and we're going to look at gear 4 as our output. So when we do that, first of all, we can see that we're going to get a negative number, right? Gear 2 is rotating clockwise, gear 4 is rotating counterclockwise. They have opposite directions, which means that the train value will be negative. And the relationship between the speeds of the two is just going to be the ratio of the number of teeth on gear 2 to the number of teeth on gear 4. So our train value here is just going to be negative 20 over 30. Which is the same thing as negative 2/3, of course. So now we can substitute in all the things that we know. We have solved for N3 is the same as the speed of the arm. Remember, gear 3 is the arm. So N4 minus negative 20. Remember, that one's negative because it's clockwise. Divided by negative 100 minus negative 20 is equal to negative 2/3. So we can solve that for the speed of gear 4, our planetary gear, and we get a positive 33.33 or 33 1/3 RPM, which, since we got a positive number, that means that this is rotating counterclockwise, which makes perfect sense given our drawing up here. Okay, so that's all I have for this video. Hope that was helpful. Let me know down below if you have any questions. Epicyclic gear trains, I think, are really interesting. You can use them to get some very complex effects. And because of that, sometimes I think students find them confusing. So please let me know what questions you have. And I just thank you for watching this video and hope to see you in the next one, where we will start talking about force analysis of spur gears.